All right. So hello, everyone. I'm Graham. So now that Al has explained what a PDF is, I'm going to build on that and explain how you get structural information out of a PDF once you have one. So my talk is all about fitting and modeling PDF. So as a big overview, there's kind of three different things you can do with a PDF. There's what we call the small box modeling. And that's just like, it's kind of like a unit cell-like description. So it's kind of like doing a Rietveld refinement in real space. There's also the reverse Monte Carlo that I'm going to talk about, which is sometimes also called the large box, which uses like very large atomic configurations to do the modeling. And I'll spend a lot of time on that because it's a little bit more complicated. And then there's also just something you can do for like amorphous materials, liquids, where you can just do a peak position intensity. And I'll talk about that a little at the end of how you handle things that are not at all crystalline. All right, so what's often called small box fitting, and usually like the programs you can do this in are called PDF GUI, and also Topaz has it. And this is the kind of fitting that we're going to do a tutorial of tomorrow afternoon. So what this does is it uses a unit cell-like description of the material and does a refinement in that. So it has an assumption of some sort of periodicity in the sample that you can define in a unit cell, and then you can do like a least squares-like refinement to produce a fit. So it's a lot like doing a Rietveld refinement like you guys were already doing, except instead of doing it on the diffraction pattern in reciprocal space, you're doing it on the PDF in real space. And so you can refine all the same things. You refine the unit cell dimensions, atomic positions, displacement parameters. And so basically what it does is it takes your unit cell and it calculates the interatomic distances between all the atoms. And it uses those as the center of a peak. And then it uses a thermal parameter to define the width of the peak. So you're basically having the thermal parameter saying how much the atoms are vibrating that determines how wide the peak is. And so this is the most common and probably easiest method to use is the small box, and it's usually what you would want to start with. So the advantages are it's quick. So usually each refinement cycle takes a few seconds to do. So you press it and then you have your answer basically. You can model like the Q-dependent dampening and broadening of the PDF really well. You can use space group symmetry to constrain the refinement, so you can keep the atoms moving within the constraints of the space group if you want. You can also break the space group symmetry when you need, if it's not, the material isn't following the space group there. And you can have multiple phases. So if you have two different phases, you can refine them both against the same PDF. Some of the disadvantages is it can't handle certain materials with a large number of different coordination environments, or where you have very complex coordination environments, because it's using just a single unit cell or a couple of unit cells to describe it. So if you have like a more complex system with a lot of different species disordered in some ways, and you can't always handle all of that. And also you can't use it for amorphous systems because it has the assumption of some sort of periodic structural unit. And if you don't have that, you can't use it at all. So here's some examples of fitting with PDF. So this is the same PDF fit over three different R ranges. So we have 1 through 10, 10 through 20, and 20 through 40 here. And this one thing when you're doing fitting like this is a lot of times you have to fit different R ranges with different models. So typically you're using the small box method for materials that are crystalline or mostly crystalline, but they may have some short range deviations from that from the crystal structure, so from the regular periodicity that you want to figure out. So you can see here in this one, you can see there's some bad fitting at low R here, particularly this peak right here. So this fit from 1 to 10 is not great, and you would need to do some adjustment to the structure in order to get it to fit. And then as you go out to higher R, if we're using, then the fit's really good. And so all these fits are done using the average crystal structure you get from a Rietveld refinement to model the PDF. So what you can tell is here at low R, there's some deviations from the average crystal structure which don't show up in the Rietveld refinement, and particularly has to do with whatever atoms make up this peak. So what you can do with this is you can then adjust your model till you're fitting this, and then you have some description of what the short range order is. And you can also then take that model and try fitting it against different R ranges, and you can figure out if those correlations are persisting. So you could have, say, like a displacement of an atom that's occurring locally that doesn't show up in the average structure. Maybe every unit cell is randomly distributed in a different direction. And then you would only have correlation up to one unit cell. Or maybe they're forming clusters of like 4 or 5 unit cells that all have that displacement in the same direction. And then it would fit up to higher R. So you can tell when the average structure starts fitting, that shows when the short-range correlations disappear. So this slide is just telling you about the different kind of parameters that you can refine in small box fitting. So you have the unit cell dimensions and the atomic positions, so that determines where the peaks are. Then you have the thermal parameters, which define the width of the peaks, like I mentioned. So those are the main things. There's a few other parameters that you need to refine. So one is called a correlated motion parameter. And so what this does is it effectively sharpens the first peak of your PDF. So when you have a PDF, as I said, the peak width depends on how much thermal motion there is. But atoms that are next to each other, when they're vibrating like this, tend to vibrate in the same direction. So they're not random. But when you have atoms that are far apart, then there's no longer any correlation between the direction in which they're vibrating. And what that does is it tends to make the first peak sharper than the rest of the peaks. And if you want a good fit to the PDF, you have to account for that. And so there's these delta 1 and delta 2 parameters, like in PDF GUI, that you can refine, which takes into account this correlated motion. There's also this Q-damp and Q-broad, which Q-damp is just how the PDF falls off just because of instrumental effects. And there's also a Q-broad, which takes into account some Q-dependent broadening of peaks. And so these are ones you determine by fitting a standard, which is what we'll do as part of the tutorial. And then you would usually leave these fixed. And if you have a particle which is spherical or roughly spherical, you can even refine the particle size in the small box fitting. Like PDF GUI has a parameter which will model the size of your particle, assuming it's a sphere, based on how fast the PDF falls off.
If your particle wasn't a sphere, say it was like a short rod or something, do you think it would give like an average size based on the size, or would it go to like the larger side?
I'm not sure, but might give something close, though your fit wouldn't be very good. Yeah, you can model all the peak sizes. Like there's something, it's called like a, what do they call it? A shape function. And there's different shape functions for different shapes. Like the one for sphere is really easy. That's why they built it right into the program. But there's also shape functions for like squares and rectangles and pyramids and all other sorts of stuff. So I think if you dig through, you can find papers which like describe those for a lot of them. You could try modeling that yourself for the different shapes. It's just not built into the one program.
Just a question on top of that. In theory, then, could you just use a much lower energy and much larger wavelength to, instead of determining the parameters of the crystal structure, to determine the parameters of the individual particles? Like if all the particles were exactly the same, they were all rods, could you use a longer wavelength to determine like the length of the rod and the diameter and things like that?
Yeah, the particle shapes?
Yeah.
I believe so. That's what c.l.s does. So Adam's going to talk about that tomorrow in more detail. So I'll let him do that because I know that it's roughly possible to do, but not my area of expertise, so I won't try to go into that. But yeah, you can. Yeah, if you go to really low wavelengths and really small angles, then you're getting same kind of diffraction effects, but it's not between atoms, it's between particles. So longer distances there, essentially. But yeah, that's the right concept. Okay, and the other thing I was going to say was with the small box software, you can also simulate PDFs, which is useful. So this is like the crystal structure fluorite, and this is just a PDF I did of that. So you can see, like I was saying before, like this first peak would be the calcium-fluorine distances. This would be the fluorine-fluorine. This one is considerably stronger because calcium has more electrons than fluorine, so you get more contribution from the calcium. And the strongest one is, of course, this one is calcium, and fluorine together. Calcium will be the strongest. And simulating PDFs can be very useful because it gives you a chance to know what to expect from your PDF. And then you can also, if you have a situation where you're thinking about doing a PDF experiment and you want to know, like if I have this structure or this structure, can I tell apart from PDF? You can simulate the two PDFs for the two possibilities, and you can see how different they are, and then you can get a sense of if you're going to be able to tell experimentally between them and where you would expect differences to be in the PDF. And this is quite simple to do. All you need to do is basically import a CIF file and then click simulate, and you have your pattern. All right. The other much more complicated but ultimately more powerful method is called reverse Monte Carlo, also RMC, which people also call the large box method to contrast it with the small box fitting. So what this is it's a global optimization method that uses really big arrays of atoms to fit the PDF. And so this method is a lot more flexible than the small box because it doesn't use any symmetry, it doesn't use any periodicity, so it can basically adapt to any local structure, and it can handle complicated systems with lots of different atoms substituted on it. It can even handle amorphous materials. But it also, because it has, tens of thousands of atoms in it, you also have to be very careful with using it because it can fit almost anything, and if you're not careful, you can get kind of nonsensical answers out of it. So I'll go a bit into how it works. So basically, you have this really big configuration of atoms, usually something like 20,000 or something is a typical type of number. And then the program will pick an atom, it will move it, and then you determine if the fit is better or worse. If the fit is better, it's always accepted. If the fit is worse, it's sometimes accepted and sometimes rejected. And there's a value called sigma, which you set, which determines how many bad moves are accepted. So basically, you have this chi-squared, which is a value that determines how good your fit is, and you get a delta chi-squared, and then the probability depends on how much worse the fit is, whether it's accepted. So as you change this, you're changing how big the chi-squared difference is. So if you have like a small sigma, then you're being pretty strict and you're not accepting many worse moves. You have a big one, then you're accepting many worse moves. So the idea is that this becomes a global optimization method. So it's still accepting some bad moves, so it can get itself out of local minima, but it's still rejecting a lot of the bad moves, so it's still overall moving towards a better fit. And then you repeat this process millions of times until basically you come to an equilibrium where the fit isn't really getting any better, and essentially the statistics of the configuration aren't changing anymore. And so this has a lot of advantages. So it doesn't use any symmetry or translational symmetry at all. So every atom is just free to move. It's fairly easy to produce a starting model. And it can come up with things you didn't imagine too. So like when you're doing like a small box fitting, basically you have a simple structural model and you're basically testing it against the data and saying, can this fit it or not? And this can end up doing things that you didn't imagine because it has a lot of freedom. You can also put multiple types of data in, which I'll go into more in another slide. And you can fit complex systems. And the really nice thing about it is you don't need to do the kind of boxcar approach I showed before with this because you have such a big box, that you're coming up with a single model of atoms, which is simultaneously consistent with the short, medium, and long range order, all in one configuration. And then you can also, of course, do amorphous materials that don't have long range order with this, which it's a little more complicated, but I'll go into it more. The bad things about this course is it's computationally expensive, so usually you need to run it about a day. Sometimes with simpler systems, you could start it when you leave work and kind of come back in the morning and it'll be done. And sometimes you need to run it several days before it really converges. So it takes a long time to set up and to run. And then, of course, while it's pretty easy to set up, the interpretation of the results is trickier with RMC because you then have, 60,000 atomic coordinates that you need to somehow make sense out of.
I have a question about that.
Yeah.
So you said it moves an atom essentially and then tests to see if it's better or worse. But there's 10 to the 4 atoms. Does that mean you're trying to converge in a space into the 10 to the 4.
Yes, basically. I should mention there's a lot of constraints in here. So like there's a maximum atom move. So the atom can't, usually it's only a few hundredths of an angstrom it can move in one step. So it's basically, it's not, jumping all the way across the giant cell.
All the atoms in one spot.
Yeah.
Okay.
So you have like maximum atom moves, and you have like minimum atom-atom distances. So they can't get too close and they can't move too far at once. So basically they're all going to stay in their coordination sphere more or less. They can't drift too far away. So that keeps it from going too crazy. But yeah, it's a huge parameter space, and you don't get a unique solution at the end, right? There's probably like, millions of different configurations. And when it's finally done, it's still moving, right? It's switching between essentially equivalent configurations, but that they have the same statistics. They have the same like bond length and bond angle distributions and stuff. But yeah. There's this one. Yeah, and so the RMC method, another thing that's nice about it is that you can use a number of different types of data as input for it. And so there's a big movement to try to do different ones. So you can have your PDF, called the G of R, and you can even have X-ray and neutron PDFs in there. You can take the F of Q, so your reciprocal space data that you made the PDF from, and fit that. So they contain the same information, but they're weighted a bit differently. You can also, if it's crystalline, you can also do Bragg peaks and have those in there. So you're basically doing a graphic-like refinement. And when you have mostly crystalline materials, that can be useful because it adds back in some three-dimensional information, because you have like you've indexed the peaks. So they have like an HKL with a relative direction to each other. And you can also add in other types of data like XFs, which adds a further constraint, which is specific to a few elements, but it further restricts it. And then I know people are also planning to add more things, and they want to add in NMR, Raman, and TM, and I think even single crystal diffuse scattering. So there's efforts to expand this to have a whole lot of data types in, even adding like a DFT calculations in with it as well. So basically you're taking a whole bunch of different observations, a giant model, and you're putting them all together, and you get out one model which is consistent with everything. All right, and this is just some examples. So this is about how to create a starting model for this. So this is an example of like a big RNC box. This is actually a smaller one. This one has, I think, about a little over 10,000 atoms, but it's still pretty big. Because you can see, and this one I think was one done before the refinement. So usually, if you were going to make a starting model, what you would do first is I usually do a Rietveld refinement on the total scattering data that you collected. So it's important to remember that you're making a PDF from powder diffraction data, and that's still just regular powder diffraction data. So you can still, if your material is crystalline or mostly crystalline, you can still do a Rietveld refinement on that data and treat it just like any other data. So the only thing is all the peaks will be kind of squished in together down here, so you don't have good resolution, but you can still do a Rietveld refinement. So you do a Rietveld refinement and you get the average crystal structure. And then basically you just expand that up. So I think this is like a 10 by 10 by 10 expansion of the basic crystallographic unit cell. And that would be your starting model. And then you would start running that against the diffraction data, and we'll adjust it to find all the local distortions. So another thing to think about when you're doing this is you have to pick weighting of your data, and constraints are both very important. So I mentioned before that there's a sigma which you have to pick, which determines how many, what percentage of the fits that are worse get accepted. And you need that to be good, because if it's really restrictive and basically you're not accepting any worse fits, then you're just doing like a convergence to the nearest local minimum, and your fit might not be very good. If it's really big and you're just accepting, like 99% of all the moves, and you're just moving atoms around and you're not actually fitting your data. So you want to get it somewhere around 50%-ish roughly. I found usually anywhere between 30 and 60% is kind of okay. And when you first start it, it's going to accept almost every move, right? Because you have all your atoms stacked on top of each other. You basically have a delta function. You need to broaden it out. So it'll select almost everything at first just to broaden out the really sharp peaks. And then it'll kind of fall into something around here. And if it doesn't, then you would need to adjust it. You also have to think about, if you have multiple data sets, how they're going to be weighted relative to each other. So you want them all to be having some influence on the data. You don't want one to just dominate the others, because then you're not really using multiple data sets. And then when you're using constraints, you have to weigh those relative to the data as well. And so you need to get that right. Because if your constraints are too weak for your, are weighted too weakly, then you're not really using constraints, it's just fitting the data. Yeah.
It's also worth noting that as the calculation proceeds, you may have to adjust the weights.
Yes.
Because your initial models might fit one kind of data set pretty well, and do a terrible job on one of the other ones. And as it proceeds, the bad one will tend to get better. And so at that point, you may want to reduce its weight so that it's not still overwhelming the other one. That kind of thing. You have to sort of keep balancing them out as time goes on.
Yeah. Yeah, with the constraints, you want those to be weighted relative to the data, so it's taking both into account. You don't want it to just, go straight to your constraints, because then it's making a model that's just what you think it should be based on the constraints you set. Or if you don't have them too weak, then it's just fitting your data and you're not using constraints. You want it to be fitting the data while still using the constraints to kind of guide it and keep it reasonable. And I think the next slide, I talk about the types of constraints that you can use in the RMC. So what these do is they help guide it. So it's kind of moving a realistic way towards a better fit. They also help keep your configuration realistic. So RMC is kind of an under-constrained method. So usually you can sometimes get some things that will fit the data but aren't really chemically reasonable. So if you have these kind of constraints properly weighted in there, then they'll kind of make sure that you have a configuration that fits the data and is still chemically plausible. But I think my favorite ones are probably the bond valence sums, because they're very flexible. Basically, as long as every ion has a proper total coordination environment, then it's happy. So it doesn't make a lot of assumptions. It just means that everything has to be basically chemically reasonable. You can also put distance windows. So if you have nearest neighbor atoms, you always have a restraint that keeps them from getting too close, but you can also keep them from getting too far apart. You can make sure you're forcing them to stay neighbors. You can use interatomic potentials. This is kind of like bond valence sums in that it basically puts the nearest neighbor atoms on springs. So it can be useful for keeping things reasonable, especially with atoms that are weak scatterers. But it does tend to force a Gaussian-like distribution, which is not always the case. And you can also use bond angle constraints. So these are kind of useful for keeping polyhedra intact. And you can also then, if you use them, you can get the angle distributions out. And so one other thing to talk about with constraints is that they're particularly important when you have an atom in there that is a very weak contributor to the total scattering of the material. So if you have some light atoms in the presence of heavy atoms, those light atoms won't contribute very much to the experimental PDF, and so they can just kind of like get smeared out in the RMC without that are causing any problem. Like if you had some lithium or something with some heavier transition metal oxides or something, the lithium makes very little contribution to the PDF. So having some bond valence sums to make sure that it stays reasonable is useful and more important than it would be for heavy atoms. All right, so this is some examples of the kind of information you can get out of RMC. So this is an RMC I did a long time ago on this supposedly cubic high temperature double perovskite here. And so one thing you can do once you have this giant configuration to try to make sense of it is you can collapse it back into a single unit cell. So this is a compound which had a whole lot of, a giant configuration like I showed before, and it's all collapsed back, so you can see where each atom would be within that unit cell. And so you get these kind of clouds of atom distributions. So the nice thing about RMC is these could end up being any shape. They could end up being kind of spherical or ovals or plate-like, or even I've seen a case where they're kind of like triangles. which something you really would never observe from doing a small box method. So you can see in here these green aluminum atoms, they're just these small spherical clouds. So they're not, they're pretty much just staying on their site and vibrating a little. And then you have these other things like the potassium are much bigger clouds. So they're spread out kind of more in a spherical way. And then the fluorines have these like plate-like configurations. You can see they're going a very big displacement side to side, much more than they are along the bond distance. And you can get bond distance distributions out for all the atoms. And so this is from one of the potassium positions to fluorine. So from the average crystal structure, you would expect a single Gaussian centered where this line is. As you can see in here, you get a much more complex distribution. You get kind of like this triple bump where the three sides are not equal in size. So this is something that you would not be able to pull out of the small box method. You can also get bond angle distribution. So from the average structure, we'd expect the bond angles to peak at 180 degrees. You can see that actually they're peaking around 165 because these fluorines are displaced so far away. And so this is the kind of like detailed information you can get from the configuration, basically pulling out statistics from all the atoms here. So here's just an example of a project I did a while ago. And this is actually a neutron PDF here, but it's still relevant. So this is like basically a cubic perovskite, because you know the perovskite. So basically you have the iron and the manganese disordered over the same crystallographic site. And you have oxygen where 1/6 of the oxygen are missing. And so from basic crystallography, it just looks like a simple cubic perovskite with a random distribution of these and random distribution of oxygen vacancies over the oxygen site. But locally, it's a lot different. So if you try to fit it, you see very quickly, like based on the cubic structure, you'd expect the first peak here to just be a single Gaussian. And it's obviously a very different shape than that. And even when I fit it with RMC, with just random distributions of iron and manganese and oxygen vacancies, I got a kind of bad fit. I had too much intensity here. And that was because the oxygen distribution is not random. It's actually depends on the atoms it's between. So you actually have in this compound an average higher manganese coordination number than iron. So the oxygen vacancies tend to occur between the iron atoms more than they do between iron and manganese or manganese and manganese. And so that actually makes a difference to the fit. And so I was actually able to figure out the different coordination numbers approximately for the iron and the manganese, and then the distribution of the distances for iron and manganese to oxygen. So actually separate them out, even though they're on the same crystallographic site. And you can see the iron here is kind of pretty close to a Gaussian. The manganese is not. It goes, it's a little longer average length, and it has this tail out here. And this is because it's manganese 3+. And even though you don't see it in the crystal structure, locally it's Jahn-Teller distorted. So it has some long manganese oxygen distances locally. And so this is an example of something you can do with RMC that you really could have done with the small box method. All right, I just have a few more. So I just wanted to, near the end, talk about liquid and amorphous materials a little bit. So this is a PDF of silicon oxide. So you can see with amorphous materials, they always have some short range order. So you can see you have a sharp first peak from silicon-oxygen distances. And then you also have a sharp peak from oxygen-oxygen distances because you have these SiO4 tetrahedra, which are very rigid and very regular, even though they're not long range ordered. Then the angle between those tetrahedra varies a little bit. So it doesn't have long range order, but you can still see you have kind of two broad humps out here because there's a range of angles, but it's not completely random. So you have some correlations here, and then it dies off very quickly and becomes flat. And so you can model stuff like this with RMC. So it's a little bit trickier to build the giant configuration because you need it to not have any long range order. So there's different ways to do that. There's different ways to kind of scramble the atoms and then move them around so that they all have the proper coordination number and then start fitting it to the data. Sometimes people also use like computational models as starting materials, like from DFT or molecular dynamics. The other thing you can also do is just simply extract the intensity of like the first peak. So you would convert to the R of R function, the radial distribution that Al talked about, and then you can just integrate the area of the first peak if it's just due to one type of atom-atom pair, and that will just tell you the coordination number, and that's quite quick to do. And this is just an example of something I did with that here. So this is this zirconium hydroxide, which, and this is the PDF. You can see it has no long-range order. It has like, you know, a little bit of order up to about 12, and kind of some moderate order up to about 8. So what I did with this was I took this first peak here, which is just from zirconium oxygen. I converted this G of R to an R of R, integrated it, and I figured out that it had a coordination number average of about 6.3. Then I made a large box, and I used like an average coordination constraint and just moved the atoms around without even fitting to the data, just to create a model that had this coordination number that I got from integrating the peak. And then I fit atoms against it. First, I had like a large sigma so that it let a lot of bad moves be accepted, and also it had large moves so that it could kind of readjust because it was a pretty bad starting model. And then once it became kind of close, then I ran it again with smaller moves and smaller sigma until I eventually got a good fit. And then I was able to extract like statistics out of the thing about coordination numbers for different atoms and bond lengths and bond angles and stuff, and develop the kind of a typical local environment for a zirconium atom in the material. All right, so this is just a little bit about the future of RMC. So there's, I don't think this is released yet, but there is a paper about it. So there's efforts to increase RMC to basically refine entire nanoparticle sizes for large atoms. So basically they rewrote the program to do parallel computing using GPUs to speed up the computing. And so, and also add in handling of instrumental dampening and broadening. So they should find larger R ranges in your data, and you can fit data up to like around 10 nanometers. You could actually fit the data out to about 100 angstroms, where now you can usually, you're only fitting about out to 40 or 50 with RMC, just because of the size of the boxes. And then you can also see like, this is a real interesting paper if you're interested in it about like actually looking at different regions where you have, you know, on like tens of angstroms of scales of like different tilting distortions in a perovskite, where they found that they could actually recover that after running RMC for a long time. So yeah, so RMC is moving towards refining up at the nanoscale, looking at much larger configurations. And the last thing I want to mention is that you can also, there's also software. There's this program called Discus. It's not easy to use, but if you're really interested and you want to invest a lot of time into learning it, you can actually simulate entire nanoparticles. So this is useful, like we were talking about before. You can actually build nanoparticles of different sizes, and you can see how the PDFs fall off based on the size. So like if you have a long rod, then the PDF falls off pretty quickly at first based on the distance across here when that dies off, but then it persists for a long time because of the long range. And then all these different shapes have different fall-offs. And you can also do other stuff where you have a single nanoparticle, like you can put capping agents on top of it, and you can simulate how that's going to add into the PDF as well and what its effects are. Okay, that's the end anyway. All right, so that's the end of the talk. I'll take questions now.
Thank you. Questions? Abraham? Oh, everybody knows that.
So I have a question about the manganese and iron oxygen vacancies that you showed. Like, how did you came to the conclusion that it's more between iron than manganese?
Oh, well, that was actually, I didn't want to get into that too much because I hadn't talked about neutrons. But with neutrons, manganese has a negative neutron scattering length. So like it makes negative peaks in the PDF, and iron has a positive one. So it makes positive peaks. And the iron has a stronger magnitude. Like iron, I think, is a scattering length of 9.45, and manganese is negative 3.73. And so overall, this peak is positive, but it's basically the difference between a positive iron oxygen peak and a negative manganese oxygen peak. And you can see here when I tried to fit it with just random oxygen vacancies, there's this like overflow of intensity here. You know, there's too much intensity, so like there's nowhere for it to go. If it went here, then it would still be too much. So basically, I could fix that by increasing the number of manganese oxygen distances at the expense of iron oxygen distances, and that reduces the intensity of this peak because you're making the negative manganese oxygen peak more intensely negative and the iron one less positive. And so by coming around these numbers, then you get the proper total intensity for the peak. And so once I had that, I was getting the proper total intensity, then RMC can actually fit it, right? Because if the total intensity is too much, it's always going to have a problem. And then once it actually was able to fit it, then it came up with these here. And you can actually show too that like if you put like the baseline here, it goes something like this. And this peak actually drops below that 4 pi rho 0 baseline. So it actually is a little bit of a negative peak here, which is from this.
And can we do it with the data that we collect from an X-ray source?
Maybe. I mean, you could. It would be less sensitive, right? Because you would have, not with iron and manganese, you couldn't because they're right next to each other on the periodic table, so they're going to scatter very similarly. But if you had two atoms that were quite different in the number of electrons they had, you could. It wouldn't be as much contrast because it's, you know, a positive one versus a more positive one. And so there would still be an effect. You know, like the total intensity would depend on the ratio. But with this case, because of the negative value of the scatterer, it was very pronounced. So if you had really good data and a big contrast in the weight of the atoms, you might see a little effect, and you could try to, you know, adjust it to match it, but it wouldn't be as precise. Yeah.
If we change the atom scattering factor obtained from X-ray to atom scattering factor obtained from electron scattering, can we do the same calculations for diffraction patterns obtained from TEM, i.e. electron diffraction patterns? Because they're basically, they look the same as X-ray patterns.
Yeah, I never thought about that, but I think that should work. Like you could simulate what you would get from an electron PDF.
Because in some metals, for example, some precipitates form with long-range border or short-range border. So if we capture diffraction patterns of those short-range border precipitates in TM and do the same calculation on them, then we can extract the average from the patterns. But we need to change the scattering factor of X-ray to electron.
Yeah. Yeah. I mean, people haven't done. I think there's been a few papers recently on people doing PDF on electron diffraction. It's much trickier to interpret the intensities correctly, so it's not widely done yet, and I haven't looked into it very much.
One slide you mentioned is mainly being done on neutron X-ray, and there are ongoing works on TEM.
Oh yeah, I think that was not TEM PDF, but just actual more like the single crystal diffuse scattering that you get from the TEM image. I think is what they were doing with the TEM there. So you have like a single crystal like you would do for like electron diffraction, and then of course if it's a somewhat disordered material, you have like diffuse streaks between the peaks in that electron diffraction pattern, and modeling that diffuse scattering in the single crystal electron diffraction pattern, I think is what they're intending to add in with the other types of RMC fitting.
So I have a question on your slide of zirconium hydroxide.
Oh yeah.
So the coordination number is fractional. So is it because it's an average number?
Yeah, it's an average number. So they all don't. I think it's basically most of them are 6 coordinate and some are 7. So like the like if you have zirconium oxide 0, 2, then the zirconium are all 7 coordinates. So I think here they're usually 7 or 6. I think probably there might be a lot of, you know, like terminal oxygen that aren't sharing there. So yeah, it's an average. So it's 6 or 7. It's a mixture, probably 6 and 7 coordination.
And why there are two other peaks for its sharing and corner sharing, the zirconium.
Why there are 2 peaks for
Yeah.
zirconium? Oh, because the zirconium polyhedra can be connected either by sharing corners or sharing edges. And you get 2 distinct differences. Like if they share an edge, then the zirconium tend to be closer to each other. That's what this first peak is. It's the edge sharing ones. And then when like these two, or these two, which is more common. And then you can also have ones that only share a corner, like between these two. So they just have 1 oxygen in common. And that distance tends to be a little longer. So here. And so here I was comparing, so you can see that this red one is zirconium oxide. So after you heat it up, it decomposes into zirconia. And these are the peaks you get. So you can see the hydroxide has the same types of peaks, but you can see that the corner sharing is less relatively. So the total coordination is less in both, but this drops by about half and this drops to like a quarter. So this one is mostly edge sharing with a little bit of corner sharing compared to the oxide. So it's usually, I think, like in this hydroxide, about each zirconia has an average of 5 neighbors. Zirconia neighbors. About 4 of those are edge sharing, and about 1 of them is corner sharing. Where in the oxide, it's 7 edge sharing and 4 corner sharing.
Any more questions for Graham? Yes.
I just have a general question. Does the temperature of the sample, and this is just a PDF question, does the temperature of the sample affect the widths of your peaks? Like if you had it at cryogenic temperatures, would you have much narrower peaks than if it was like really hot?
Yes.
Okay. Is that desirable in any way? Do you have to know what the temperature is specifically, or does it not really affect it as much?
It's not so important for modeling because you just refine a temperature parameter and it will fix it. Mm-hmm. But it can be useful to measure things. Sometimes people do measure PDFs at low temperature just to make the peak sharper. Like if you had 2 different types of atom pairs that are very similar. So you had like, you know, iron oxygen and ruthenium oxygen, which are probably differ by like, you know, 1 or 2 tenths of an angstrom or something, and you wanted to tell them apart, then you can try to get really high Q data to reduce the instrumental peak broadening, but you can also cool down to low temperature to reduce the thermal peak broadening. And so sometimes that cooling down may help separate features that are very close and may blur together at higher temperature. But if you're doing high temperature PDF, it can be a problem. Like if you're doing like a PDF at like 800 degrees Celsius or something, you know, even if all your experimental, you know, instrumental broadening and you have a very high Q, your peaks are still going to be pretty broad just because the atoms are bouncing around so much.
Okay.
But yeah.
Any more questions? You will find him in the afternoon tomorrow if you want to do something. Thanks. Thank you, Graham.